Hi everybody, this is Aaron Murakami with the recent Bedini-Lindemann 2013 conference in Hayden, Idaho. And you might know me from Energetic Forum and Energy Science Forum. And myself and Peter Lindemann have been publishing some different books and video presentations through emediapress.com, and which is where the different presentations from the conference will be made available. So right now, this is July 15th, so we're about a week, actually 2 weeks from the conference, which we had on June 28th, 29th, and 30th. If you do want to see a little bit more about what that conference was about, who the speakers were, what the schedule was, you can go to energyscienceforum.com, and at the top of that there's a banner for the conference you can click on, and that'll take you to all the speakers' bios and everything else. Sitting with me here is Mr. Paul Babcock. He is the founder of Flyback Energy. And if you know about our conference last year, which was about the same time of year up in Hayden, Idaho, Paul gave a talk called Magnetic Energy Secrets, where he went over some of the technologies he's been involved with, different experiments using plasma over an arc, using inductor, with an inductor, without, showing, for the same amount of input you're putting in, you're able to get more work done, burning down a copper rod.
Hotter arc.
Paul,
more energy.
And so, and this year you went over a little bit more about that. And one of the differences from last year is you alluded to a motor that you're working with, because your company has, when I first met you, it was several years back, and you were still in the process of filing for some patents on your switching circuits and that motor.
Yeah.
So you couldn't really talk a whole lot about it, or even mention very much last year.
Yeah, at least till the patents were published.
And so
once they're published, then I have no problem talking about it.
Right.
Because it's public information after that. So.
Right. And so so if anybody goes to a patent database, and if they want to see some of the switching circuits and the motor that Paul is involved in, you could type your name, Paul Babcock, as the inventor,
Yeah.
and it should come up.
Yeah, exactly. It always comes up. Yeah. And
Right.
there's about 14 patents out there, but
Yeah.
spread around the world. But the three main big ones always pop up first. So.
And are those patents mostly related to the high-speed switching circuit you developed and the motor?
Architecture, it's electronic architecture was the first one. That's the first one we had to get done because everything's based in that. And then we had what was our mini microgrid technology, some of our inverter technology that we took that switching and created, and our mini microgrid, and a bunch of our technology that we integrated. Very extensive patent, about 80 pages. And then the real third one is the motor patent, which is where we take that same switching and use to create the externally coupled motor that we developed. And so they're all out there if you sort through them.
Right.
Sometimes the patent office makes you pay for the drawings now, but they're there and all the claims and everything. So
Right.
it's time to let the world know about it now. So it's not, the patent world is a world unto itself,
Right.
And
So with the motor, for example, like last year, you just kind of talked a little bit about it, but since the patent's been granted
well, it hasn't been granted yet, but it has
okay.
been published, yeah.
The application is published.
Yeah, exactly.
Okay, and since that is publicly available and people can actually see it, at this year's conference, you actually explained a little bit about the operating mechanism behind it and why it's.
Yeah, there's bunches of different mechanisms. Well, we spent years in the lab, and we built that one, in our home labs, and we built that motor to express everything we had learned in one device. And that motor has actually, now we finished it in early 2003, so it's been sitting there for 10 years. But we thought we'd be able to go out into the world with that motor explaining everything, and it really just befuddled. It was just, it really, we really got beat with and pelted with rocks more than we got a warm reception over it because it was so radically different. And, the claims that we were making about external coupling and, the whole concept is that electricity can be used multiple times. You can make work with electricity, get that electricity back, and make work with it again and again and again.
Right.
So it was built to prove that concept.
With just a little bit of losses, so you just make up for the losses.
So we're making up for the losses.
Right.
And also about beating Lenz's law and taking out drag forces out of motors, right? So it was all about rearranging Maxwell's equations.
Right.
And Faraday's and Lenz's equations and saying, hey, if we can externally couple, figure out how to get the same foot-pounds or equal to force out of a motor, by driving externally coupled fields, if we can get enough foot-pounds, that we can actually build different motors with different curves, right?
Right.
To where if we don't have drag forces, we can actually increase the speed of the armature because it's clock driven, it's not voltage driven like a standard motor is. You turn the voltage up, it goes faster. But of course, so does your watts. So we fire the coils of a high frequency pulse, which gives us, and it's pulse width modulated, so it gives us a very precise torque control.
Right.
But when it comes to making the armature go faster, we turn up the clock speed. We don't turn the voltage up, we turn up the clock speed.
So it's the same going in.
Yeah, so we maintain the same torque, but as the RPM goes up, the horsepower goes up. So so we flattened out the curve. We actually do have a little bit, some drag force in there. We got about 80% of it gone, and if we had it perfected, it would probably be even much more efficient than that. But we showed how we can make things go faster and faster, increase horsepower. With very little inputs, increases of input power, which of course that was a good beating from the academics over that one. And then we recovered all the energy off the coils, or 50% of the energy we recovered off the coils. So we have videotapes. In fact, I was going to do them at the demo, but I couldn't find them. Of about how we actually have the motor set up to where we can actually feed the power recovery out of the coils out to resistors, and you can measure that power. And you know, they get hot, plenty hot. And then now we just flip switches and we reroute that power back to the input to the system. Now the power just drops down 50%, but the load maintains perfectly.
And so in simple terms, a lot of people who have you know, followed the so-called free energy field and looking at these, you know, exotic energy technologies, is pretty well known by this time by a lot of experimenters that, you know, you can charge a coil, get work, turn it off, that field collapses, and normally you'd get a spike out of it. So instead of that, you're able to do something special with that spike and control it to do more mechanical work.
Exactly, and recover energy at the same time. So if you let that spike go, you know, if you just turn the circuit off, what you get is that high spike of energy, a high voltage, low current, high voltage spike, because it's all about the velocity of the field collapse. It's dV over dt, you know. Faster collapse, the higher the spike. So we created this high-speed switching system. The magnetism is fast, right? I mean, you got to be fast to get a switch connected to that. So otherwise, that energy's transformed itself to high voltage instantly, right? I mean, it's, you know, so if you're not faster than 50, 100 nanoseconds to get a full, what we call our capture circuit, we call it fire and capture. Fire is energize it, and capture is to grab that energy that's built up in the coil. So we figured out how to make that switching transition from fire to capture in a matter of nanoseconds. So what it is, the voltage never gets to shoot up to that high voltage. So we actually dump it onto a capacitor and give it a low impedance load. It's always the same joules, whether it's a high voltage low current or a low voltage high current, but we give it just the right load to where we control that collapse and control that voltage level.
So it collapses slow, but the current is still there.
It's still, that magnetic field.
So the magnetic field is there to push or pull the magnet, whichever way it's
so we're getting work out of it, right? And then while we're doing that,
which means it's disconnected from the input.
Yep, we're getting work while we're disconnected from the input, right? We're making that field still perform work while it's collapsing. But we're also charging up that capacitor. And so the trick is to charge that capacitor up to the right level to where we're 20 to no more than 30% over the input voltage. And then right in the beginning of the next cycle, that capacitor discharges first before we draw from the input power. So all that magnetic field is constantly circulating back in. It's performing mechanical work, and then it puts, and so while it's doing that, while you're disconnected from the source, then on the beginning of the next half cycle, it dumps that cap and performs mechanical work again before we dump on the source. So both ends of the waveform are work that's built into the coil rather than just 100% from the input source. So it radically jumps up efficiencies.
So you're like double, triple dipping into the same stuff.
Exactly. We're making it work. We're making that field work even after we've disconnected from the source.
And so taking that capacitor and being able to put it onto the coil fast enough is where your patented special switching circuit comes in.
Exactly.
So,
and we also had to make it tough enough because we run big inductors. That's why high frequency switching came along. is because if you take your average transistor and you hook it up to a big inductor,
Right.
that magnetic field just turns around and eats your semiconductors.
Yeah.
It was why high frequency switching came along, because nobody could figure out how to run big inductors reliably with transistors. So that's why we created our switching architecture to where it actually duplicates mechanical switching. So when it's off, it's off and it's high impedance. So when that field collapses,
Right.
it's tough. It can live through those big inductors, because
Right.
I mean, we run big inductors.
Right.
We don't mess around. We got big transformers and
Right.
big coils
Right.
and while we were developing this, a lot of different stuff came out about it, magnetics, that's just not taught in the books. Like it's what we call reduced impedance effect and other things. So reduced impedance effect is there's two ways you can make magnetic fields. You can run lots of current through wire. You can run, the more wire you have spun on there, the stronger your field, or the more current. The problem is with more wire is you get inductance, and then when you try to put high frequency pulses through it, it rejects. So you can't build up the old way was you couldn't build up a high, strong magnetic field from lots of wire, because you have the impedance, good old Henry's opposing your input source, so you couldn't get any current through it.
Right.
But with this high-speed switching system, we call it zero stating the inductor, where when we de-energize that puppy, Mother Nature gives you a freebie. The very first pulse, it'll let you run current through it until you get a magnetic field built up that turns oppositional to you. Just good old Lenz's law, it's just bucking against you. It's Henry's. And so that first one's free.
Right.
But after that, it takes voltage to drive current, and then and so you can't use lots of wire to make a magnetic field. So what they do is they shorten the wire up and run lots of current to get the same magnetic field. So more current, more watts.
Right.
So we went out to prove that we could put lots of wire in and create really strong magnetic fields for way less electrical input.
Right.
And that's what the reduced impedance effect was. So like the coils you see in that motor, there's 1,500 feet of wire, a nice steel pellet core in it. But those are 300 millihenries. And if you take them and plug them into a 60 cycle AC socket, they don't draw a milliamp because of the impedance. But yet we run them at 400 hertz.
Right.
At 160 volts, we can run like 3.5 amps into them with pulse current.
So,
And so how does that happen, right? Because reduced impedance effect. So now we got the current through the thing, but we got lots more wire, so we get a lot of magnetic field for less actual energy. And that's how we could build up 16 foot-pounds of torque in that thing and still have a 400 hertz pulse width modulated system.
So,
And you don't
right.
see that in the textbooks.
Right. So the principles of all these concepts coming together with the switching, with the sequence of events that happens in your electric motor. So a lot of these are explained in last year's conference up to a point.
Yeah.
In the original Magnetic Energy Secrets presentation. And then in this one, you basically start off right where you left off last year.
Yeah.
Kind of go into that, giving a lot more of the step-by-step sequence of what's happening in the motor.
Yeah,
that kind of stuff, and that's what
and some
people will
drawings
learn.
out of the patent that shows
Right.
the external field coupling. And,
Right.
there's like I said, there's about 5 things in there that all work together to create the concept.
Right. And you even showed a small, a short video clip of the motor running on one of the tests you guys were doing. And
Yeah, that was at its top speed run there. That's about 340 RPMs, but the heads are actually going about 70 miles an hour.
yeah,
So,
right,
and you could use it for linear motors, maglev trains. We just built it to prove all these different concepts that advance electromagnetic science.
right,
And that's why we incorporated it all into one device. And 10 years ago the world wasn't quite ready before it, but now I think
right,
things have broke loose a lot. And,
Right.
so that's why we're going a little more public with it and getting it out there. And it's
Right.
brought a lot of inquiries to us that
okay,
which is great.
Right.
Because we want to we just had to get our intellectual property ducks in a row to a certain point
Right.
before we could do that. Because we give our patent attorneys heartburn when we
right,
get out there too soon. So
right. Now, I do have some questions here, but before I go into any of these questions. These are actually questions written up by some attendees at the conference. We are going to have a discussion panel with all the speakers, and Gene Manning was going to moderate that discussion panel. Kind of ran out of time on the last day, so we weren't able to do it, but we still want to get everybody's questions answered. Some of them are general, you know, to any of the speakers, and some of them are specific just to you. But before I go into those, did you discuss in the presentation at last year or this year's conference about the core material you're using for that motor?
No, actually, I don't think. Well, I might have mentioned it briefly, but I
Okay.
didn't go into in depth of it.
Because that seems so simple of a thing, instead of having to spend buku bucks on exotic core material and stuff.
Yeah,
You have
exactly.
a simple solution. Is that something that you're
Oh,
looking
I'd be
to-
glad to share that, because
Okay.
shotgun pellets are awesome. Because
Okay.
see, when we started out, we started building a motor in 2000, summer 2001. We had about a $200,000 budget. You know, we got a business loan, and so we were gonna, you know, farm out the parts and you know, have the cores made and the coils wound and hire a programmer to do it. Well, when the airplanes hit the building, all our, you know, magically all our bank funding just got pulled out from under us. So we had a credit card, a business credit card with $20,000 on it. So our budget went to 10%.
Right.
So it was like, you know,
I guess the creativity going.
bubble gum,
Right, Scotch tape.
Scotch tape, you know, epoxy glue. We couldn't afford to get our circuit boards made, so we literally cut every board, drilled
Right.
every board, stuffed every part, you know, built up the electronics to it. And then for core material, we were like, what are we going to do now? Because getting the cores manufactured was a pretty spendy bill. It was about 10 grand.
And were you looking at any special materials, or?
We were just using silicon electrical steel, but we're going to have it stamped out, you know, and molded and pressed, you know.
So it is a standard industry material.
Standard,
that's-
yeah, silicon electrical
Let's
steel.
go with the magnetic field fast and.
Yeah, well, they put the silicone in it to make it highly resistive, so it cuts down eddy currents.
Okay.
But what you really want in the core material is carbon-free iron,
Carbon-free iron.
because carbon is what makes steel, and the more of steel it is, the more retentivity it gets.
So it's holding on to the magnetic
holding
field.
onto the magnetic field.
So it's a slow release. Like when a switch goes off, it won't collapse as fast as it could.
Exactly. Well, yeah, so it maintains a magnetic field. It just doesn't go back to, you know, you want it to go magnetic, highly magnetic, and then when the current goes away, you want it to go right back to scrambled iron molecules. You don't want it to stay in any crystalline form, because that
Right.
makes hysteresis and drag force. You know, it eats up your power, because you're always having to buck the magnetic field that builds up in that iron.
On the next pulse as
On
it's
the
coming,
next pulse,
right?
yeah. So I was looking for some easy way to
Right.
figure it out, and then, you know, being a sporting guy, you know, I just did, I remembered this article about shotgun pellets and how they had to make the steel shotgun pellets really soft by, they call it carbon-free steel, which was what I was looking for. So, you know. So I just got to looking around on the internet, and I ordered up a couple of tubes. I mean, they're cheap. I can't remember. I think I paid like $10 for 20-pound, you know, 40 pounds of it.
And those are pellets intended to load your own shotgun shells.
Exactly.
Right.
And they're steel pellets, but they've got to be as soft as they can make them, so they don't hurt your shotgun barrel. So
So it doesn't scratch and stuff.
yeah, so it's not hard. So like the lead will actually compress and form to the barrel when it goes out. So they had to have the steel do the same thing. So they take all the carbon out of it, so it's really just pure iron with no, I mean, the purest, softest iron they can make. Then you put this micro layer of zinc on it to keep it from rusting, and the zinc is meaningless. So we ordered some of them, and I took a neodymium magnet, and I just stuffed a handful on there, and let it sit to get it good and magnetized.
Right.
And then I pulled them off and put them on a nice flat plate and rolled them around, and it didn't stick at all. Right?
They just all rolled apart.
Yeah.
Yeah.
I mean, no retentivity whatsoever.
Uh-huh.
So it was like, all right. So then we just took them and we roll them out on a flat piece of cardboard, like a cardboard box, and just put one layer of quick acrylic from, you know, Home Depot acrylic, and that puts that coating on that breaks the conductivity between the pellets, so you don't get current pass between the pellets. And then it's just pour them and mold them after that. And
What size pellets are they?
They're
How are
they're number 7, the smallest we can find. You can find them from
Uh-huh.
buckshot down. Number 7 was the smallest I could find.
what is like a millimeter diameter or something?
Yeah,
Or
about a
what's-
millimeter. Yeah,
Okay. So
and
carbon free number 7
birdshot.
birdshot. That
Steel
you get at
birdshot.
any sporting goods store
any
or,
reloading
right,
outfit.
Cabela's and those kind of
Cabela's,
stores.
yeah,
and-
you can order it off the internet. Cheap
Uh-huh.
can of quick dry acrylic.
So just one coating is enough.
Yeah, one quick coating, roll it
Right.
around, and then
Right.
and then you can pour a tube of it and you can stick your
Right.
probes in there and zero conductivity, really high impedance.
Right.
So that breaks up that's what silicone, that's what they do in any kind of core material. They make thin layers
Mhm.
and put a insulated material on it so it breaks the eddy current paths.
Okay.
So I found those little tiny pellets,
Mhm.
just made coated with acrylic, it just made an
Right.
outstanding core material. In fact, we built a couple of schoolgirl motors last winter in the shop there.
Some SGs using that
Yeah,
in the
uh-huh.
in the coil.
Oh yeah, it worked great.
Right. Right.
Easy,
Right. Inexpensive.
inexpensive,
right.
easy, and you can mold them, and you can make, you can pour it like for our big coils, we'd take like a gasket, real thick gasket material, and we'd just cut it and set it inside the core and push it out, and then glue it, and then just glue bottom plates in it and fold it over, and we just fill it up with pellets. And you can pour a little epoxy in there if you want. If you add some epoxy to it when you build it, it makes them hard, nice and hard and stiff, so you don't have to worry about it.
Right.
We did the same thing when we built the cores to our motor. It was actually just thin cardboard core, and we just set it on a piece of wax paper and pour a little epoxy in the bottom, and then pour the pellets in it, little epoxy pellets, little epoxy, and
Right.
top it
So
off.
just did it a few layers at a time.
Yeah.
Yeah.
And the epoxy just runs right down through the pellets. So if you get some not too quick of cure epoxy,
Right.
because it doesn't set up on you too fast. Hell, by the time when you get it done, it's just a beautiful solid piece
Right.
of iron and makes
Right.
a great core material.
Well, I'll go ahead and go into some of these questions here.
Yeah, that's
and
fine.
then let's see. Okay, so this one is addressed directly to you. How does the plasma in the circuit aid in the capture of energy? Which anybody who gets the presentations will be able to see what the plasma stuff is about. So how does it aid in the capture of energy?
Well, that's the funny thing about plasma, not being a plasma expert. It took me a long time after, I read lots of Tesla, Newman, read all this stuff, and they're all right. But the plasma thing, when we were doing those experiments, was really kind of one of those just out of nowhere discoveries. How the hell did my arc get so
Right.
damn strong?
Right.
So we started experimenting. We had a number of different coils. We had 1,000 footer, a 1,500 footer, and we were really studying our reduced impedance effect, making longer and longer and longer coils. But we're also realizing that, man, when we started testing them with DC, we just started realizing that, man, when you got those big coils, we were getting these really long. We started playing with DC, just running DC through them, and we started realizing that, man, when we get a plasma arc, and we'd seen this all through our industry too, right? Because we're all DC engineers, right? Doing big power systems and phone companies, and you get lots and lots of cable out there, and like when you're in a central phone office and you're hooked up to like 4 acres batteries, and you
Right.
short the cable out. You just find the longer the cable, something we all notice for 30 years, the longer the wire, the bigger the arc. And, you ask my 2 partners who are, Bellcore level 4 certified DC engineers, they've seen steel racks cut in half and stuff, but it seemed beyond Ohm's law somehow. Somehow things just didn't add
Something
up.
different was going on.
Something different was going on. So that's why we started doing resistance compared to coils of equal resistance. And we just found that consistently we could make that arc bigger and bigger and bigger. And
Right.
Ohm's law expression exactly the same between the resistor and the coil. And the difference was it's the length of the magnetic path.
Right.
The longer the wire, the bigger the arc. Just like we discovered out there in the world. You got 400 or 500 feet of big cable out there, and you short something out, and it's still only 48 volts, but you can get 10, 20,000 amps. That all of a sudden things would just vaporize.
Right.
you pull arcs that long and blinding and pieces of molten, digging out the pieces of molten copper out of your skin and stuff.
Mm-hmm.
So we started experimenting with that and realizing that, and then doing the burning the rod, that we could consistently, it was very consistent. The only time we ever found it wasn't consistent was we were having a great big lightning storm right there in the shop and we were playing and things weren't, that's the only time we ever saw fluctuations in what we discovered.
Right.
Which, if you're living in a sea of energy, that makes sense. So it took a while, and the thing is, we got all that data, and then we got back to building the motor and trying to make a business, and it just got shelved for a while until I brought it back out for last year's energy conference. And while I was up there doing the first talk, and explaining, that, hey, this happens, all of a sudden, it just like popped into my brain, oh, this is all Tesla, and I can put this to math. So between last year's talk and this year's talk, I related it back to Tesla and radiant energy. It had been seen before. It had been seen by Edison. We'd seen it out in the field, and now we were reproducing it. So then I spent some time, okay, let's turn this to algebra.
Right.
Now that we have some verifiable quantity of energy that we can see, touch, feel, quantify, well,
Right.
that's all you need is, what does it equal to? So that's why it just dawned on me one day
Right.
that it's some part electron energy, and then it's some part, it has to be radiant energy, and somehow plasma has this magic ability to turn radiant energy into light and heat. And I don't understand the physics of it, but here's like Tesla and so many other experimenters have learned, it's even like Bedini. As long as you're trying to catch it between the stops and starts of electron flow is when you see the radiant energy effect. So you're turning on and off, dragging that energy in.
Right.
Well, the plasma can continuously convert radiant energy to light and heat, which makes it useful, So it's got some, and what is plasma? It's basically, you've got an atmospheric gas that's been stripped of all its electrons.
Right.
So, basically all its orbits are down to nothing to where things just bounce through it, or you have super excited electron orbits, and they call it the fourth state or fifth state of matter. So it magically has this property.
Right.
And so that's
Highly conductive.
Very loose on the electrons. So, and Tesla said it, that the radiant energy flow, we live in a sea of highly energized particles. They have the same properties as an incompressible fluid, and they flow with the electrons, but they don't express themselves. So, I can take a light bulb or anything else, it's just a regular resistive load, and you put in series with that coil, and it's just a resistive circuit. But the second it becomes a plasma, an atmospheric plasma, then all of a sudden that thing gets 3, 4, 5 times as bigger, and I'm burning the rod 2, 3 times. So it is heat, it is light, it's a useful phenomenon, and it's coming from somewhere, and it isn't coming from electron flow because Ohm's law is still irremediable.
So I mean, it's still the whole plasma field. There's so much where that's going to go into the future. The understanding of what's going on and.
Exactly.
But at least you can see the numbers that this compared to this, there's something going on that's above and beyond what's supposed to be there.
Exactly.
And you can put a number to it.
Exactly, and that's exactly it. And once you can quantify something, you can turn it to algebra.
Right.
And that's why I related it to the length of the wire, because this is what we learned: the longer the magnetic path, the bigger the arc.
Right.
I might have a lot of resistance in that long wire, and I might have to crank the voltage up and expend a lot of watts to get that current level. And it's also I squared. It's I squared in this length of the wire. So magnetic field increases exponentially with current, right? If I double the current, I get 4 times the field. So it's about the magnetic field that lives in that wire. Somehow it becomes the translator. And it's just like a leak, almost a leak from the etheric field. When that arc translates and it goes somewhere to light and heat, the pressure's off, like you got a leak, and so now things will flow. So the radiant energy will flow, but if there's nothing that can dissipate that energy or convert that energy, then nothing flows, because there's no way but the plasma does that.
Mhm.
That's why I tell you about, you know, and anytime you have Tesla radiant energy, you see those
Right.
funny sparks. It's just like the first demonstration with your coil, right?
Yeah, they go out radially from the.
Yeah, anytime, you know, it's like your plasma amplifying car coil with the diode on it. It's exactly the same phenomenon. There's absolutely no difference. You'll see those radial sparks,
Right.
and they have their funny characteristics to them. They
Right.
run from the magnetic field rather than being attracted. Any other plasma
Right.
just gets sucked into magnetic fields.
Yeah, there's a picture that's been around for a long time of John Bedini shorting something out in one experiment. You can see these like greenish sparks going 90 degrees away from the wire
Exactly.
in all directions, like a star.
It's exactly what they're. They're
But we see
perfectly
that over and
radial.
over.
They're always at a 90-degree to the current flow,
Right.
and they run from the magnetic field rather than going to the magnetic field.
Right.
And they've got these, and they're almost like these corkscrew properties to them.
Yeah.
They're just, and they're damn hard to catch on a camera. 'Cause
Right.
they try
Right. Right.
But yeah, and whenever you see that, you know you have a radiant energy. That radiant energy is there, right? And that always relates to there's a big coil of wire in there somewhere. So, and it's just the same thing with your coil experiments. That plasma, just, you know, you take a little plasma arc, and the next thing you know, the thing is that long. So what, with your diode there, what gates it opening? It's allowing a path. You're creating plasma, so the radiant energy field is doing its thing. Plasma will translate radiant energy to light and heat.
Right.
And so, seen it my whole working career,
Right.
you know, forever and ever. So now it's just how we turn it to algebra. Now that we see it,
Right.
we know we can quantify it as energy.
Right.
What's it relate to? Length of wire in amps.
Yeah.
Simple algebra. It's almost like Ohm's law.
Right.
You know.
Okay, this next question, and I don't know who these questions are from. They didn't have a place to enter who it's coming from, but this is from Mr. Babcock or Mr. Jim Murray, which I guess was a bunch of interesting coincidence or synchronicities between your motor and his, where
Oh yeah.
separate parts of the country you're working on virtually the identical kind of motor and stuff.
Yeah, exactly.
And I'm not really sure what this is asking, but would it be possible to build a solid state circuit that pulses with a variable resistor to dial in the frequency? And ask this.
Yeah, 555 timer.
So, and I, there's a few words missing out of the sentence. I'm not sure totally what they're asking.
Well, he's
totally what
trying
they're
to create
asking,
a frequency-driven pulse circuit to drive a transistor. 555 timer driving your transistor.
but best place to start for sounds easy.
Find Sam's 1984 TTL handbook.
Uh-huh.
I've had one for years. It's like my purple. I call it my purple Bible. You know, so all we built all of this. If you're wanting to build circuits and you're not like a real microprocessor pro, 555 timers. In fact, that's one of the things I want to do is publish a bunch of our old circuits, experimenter circuits, because
Right.
I call it building blocks.
Right.
We created all the building blocks, circuit building blocks, so we could make pulse width modulators to frequency drop, to
So you
oscillator.
got all your modules to just plug together
Yeah,
and whatever.
switching
Right.
circuits, PNP and NPN switching circuits, and little power supply,
Right.
everything you need. About 50 different little circuits, and you just put them together like building blocks, and you can make anything you want to drive and pulse
Right.
anything.
And what is that book that you referred to?
I'm not even sure if they published, but it's
Right.
my copy is the 1984 Sam's Photo Facts TTL handbook.
Okay.
Totally handy.
Right.
It's
Yeah,
just got
might be
endless.
a PDF online somewhere of it. I don't know.
Yeah, I was thinking of scanning it in, and,
Right.
but we
Right.
we just use it as our base. I mean, you can build just endless amounts of stuff to,
Right.
great circuits.
Right.
Clocks, drivers, pulse width modulators, delay timers,
Right.
and you can create pretty much any pulsing driving circuit
Right.
you want. And with modern 555 timers, you can go up to into the megahertz if you want to for
Right.
drives. Then with modern, IGBTs and FETs switching components. See, back in the day, I used a 3 ohm FET would cost me about 20 bucks. 3 ohms, and I could get 10 amps in it, and that was like 20 bucks. Now I can buy a 100 amp IGBT that'll run at 200-300 kilohertz for like 4 bucks.
Right.
So we have all this great stuff.
Right.
I mean, great electronics components. That's why we had to we had our theory down years before we had the components to work with. So there's a lot of great stuff. Microcontrollers, if you can know C code or C plus code, you can buy like a free scale microcontroller, what they call them digital signal controllers. They got A to D converters and programmable amplifiers, all this peripheral circuit built right into it, and it's just plug and play and write the code.
So a lot of this stuff, at some point when some of your time is freed up, I know your business is going through growth, and you're, got to dedicate a lot of time to that. So when there's finally a time to breathe a little bit, then some of that stuff you might be able to share a little bit.
Yeah, I actually want to make a experimenter's kit. Do a video on how to build circuit boards, and there's so many tools that the experimenters have, like circuit boards. I can get a free program from PCB Express or any of these companies. You can build a circuit board, send them the file, give them a credit card number, and next day, 24 hours, there's your circuit boards. On-demand printing for... Yeah, you just go and they give you a program to cut your circuit boards, a schematic
So
builder.
They need that file to plug it into their system. And
I'm trying to think of the name of the file,
Like a Gerber file kind of thing?
It's a Gerber file, exactly what it is. So you make the Gerber file, you go bank, they say, for that board, we'll give you a dozen of them for 75 bucks, or whatever, and you go, okay, and you pay it with your credit card, and then bam, in 24 hours, 48 hours, it's at your doorstep.
Right.
And professional quality, 2, 4-layer boards, whatever you want.
So nobody has an excuse really anymore with all the resources available. That's like on-demand book printing. You upload a PDF, and you can have a paperback overnighted.
And they give you the software, the schematic build software, everything. And if you want to take it a step further, you can get the modeling software to where you can run your circuits before you ever even build them.
Right.
And so with everybody and their computer talent, you don't have to be like super engineer. And it's like. So you can make circuit boards, and a Radio Shack perf board is a great place to start too, just stab them on there and jumper the wires and go, It does a million perf board circuits, and, and with eBay, you can find oscilloscopes, you can find a nice dual trace Tektronix oscilloscope for 50 bucks.
Right.
Frequency, you just go on eBay, you can get yourself some killer test equipment, for cheap.
Right.
So the resources and tools people have to experiment now are just freaking awesome, and that's what I'd like to do a video on that.
Right.
And how to, a little bit about electronics, once you get this test equipment, you need to know how to use it. But, here's circuits you can build, there's building block circuits you can put together, you can make drivers, and you can do all kinds of stuff, And as far as our patents go, as long as you're not commercializing it, use it to your heart's content. That's legal to use patents for yourself. So we've got some great circuits that we developed, that are tough, that live through the, so how to wind coils, like we built our coil winding machine out of a $35 Harbor Freight drill press. We just pulleyed it down one step so it didn't spin too fast, and you can spin wire on coils. It's like how to make core material, and wind your coils and pour your core material in it, and poof, you got your great big solenoid coils. Right. All kinds of endless things you can do these days with the tools we got.
Right. Okay. Now this question I asked in another interview. It's directed to everybody. How to get this information into the public arena so an individual can be free in America, which is kind of one of the goals of what we're doing at the conference to begin with, where people can see it and getting the presentations out. But maybe I can.
It's kind of
how do you see the information thing going with all these kind of technologies? Because I mean,
I have a lot of opinions of it. See, there's things that are, commercializing products,
Mm-hmm.
like we've been doing for 10 years is, it's this painful road to hoe,
Mm-hmm.
to get, say, well, I want to create this stuff, I want to sell it commercially,
Mm-hmm.
so it take, depending on how, so if you got a complex electrical device, plan on, spending some millions of dollars and
Mm-hmm.
hiring employees and then
Right.
government oversight and UL and listing
Mm-hmm.
and all this stuff that drives you crazy to
Right.
get really complex, electronic systems built.
Mm-hmm.
There's that route.
Actually getting the technology manufactured
Yeah,
out,
well,
not just the information.
You've been to our lab.
Right.
You see, it just,
Right.
it took us facile engineers and
Right.
raising funding, and then it couldn't be
Right.
too controversial or even save free energy, because that's just a great way to watch your investors run for cover and scream crazy
Right.
people. So we had to find that interim step to where it's
Right.
not too radical, but it has great functionality and usefulness.
Mm-hmm.
And the idea is to get that to where that funded us, but the economy is really hard out there, and it's kind of a rigged game to keep.
Right.
You got the big companies, and they don't. Nothing scares big business like small business.
Mm-hmm.
But somebody's got to do that end of it. So to me, is somebody's got to go out there and push the commercial end of it, but somebody also has to be making it cottage industry. That's like Gene Manning and her free sourcing the information. So many inventors are just giving the information, selling their books and their CDs, and so if you go out and you're in a garage and you make 20 of them and sell them to your neighbors, it's got to be work from all ends.
Right.
Eventually, the old guard's dying out, and you just have to put it in people's minds. They have to see it to believe. If knowledge is the power, if they know it exists and they've seen it, they've heard about it,
Right.
then it's not mysterious, and it's nobody can tell them that it's not real, or they didn't even know it existed in the first place because it's so rubbed out of the public consciousness that.
Right.
So it's like spreading the word's part of it,
Mm-hmm.
the free sourcing of information.
Mm-hmm.
It's like Bedini's SG motor.
Right.
It's what a great place to start. Simple device, anybody can build it.
Right.
To me, the 21st century is going to be the radiant energy century. The one that should have been last,
Right.
the 20th century, we're going to do
Right.
this century. Because people are just way different.
Yeah, people are
However
hungry
bad-
for it.
People are hungry for it, man.
Seeing that this is not some kooky deal, but this is this is
Yeah.
real stuff going on.
Well, in the scientific community, bless their hearts, they BS people for so long that people, you can only be, what did Lincoln say, you can fool some of the people all of the time and all of the people some of the time, but you can't fool all the people all of the time.
Right.
Well, that's what it is, man. People have really come a long way in their thinking, man. And
Right.
just the last 10 years, I'm just astounded,
And all the online forums and YouTube and people
Yeah.
putting out videos. And Of
Exactly.
course, there's a filtration process people got to go through to see what's real and not. But but when you see the same names going over and over, over the years, you kind of know who's consistent in showing results and showing stuff.
Exactly. And
so-
and there you go. And go out and read the books, man. Study your basic physics. It's everybody thinks electronics is some kind of mystery science, and it's not. It's plumbing.
Yeah.
It's just electrical. It's
Right.
it works the same pretty much like water.
Yeah.
It just if you can do ninth grade algebra,
Right.
you can do 90% of the math.
Yeah.
Simple form. You don't have to get in all these extensive equations and weird stuff, especially in the digital age,
Right.
and the tools we got and the fantastic components. I mean, it's the experimenter's dream, but, a lot of people don't experiment like they used to, I mean, it used to be back in the analog days. I mean, you had to be a real designer
Mhm.
to understand analog physics and all that. I mean, you really had to be sharp to design,
Right.
radio circuits and TVs. But now it's the digital age. Everything's just on and off.
Mhm.
Especially with like the coils and the stuff we're doing. Most of it's you're turning it on and you're turning it off. Those circuits are easy to make, And so what, you blow stuff up? You just try.
Right.
Try again. I've killed so many transistors over
Right.
the years. It's like I got used to have bucketfuls of dead ones laying around, and so what? Just dead soldiers, man. Part of the war,
Right. Right. Okay, next question is, does anyone have experience with cold flames, and are there any useful devices that use or make it? Have you ever seen any
I don't know
so-called
exactly
cold
what he's calling a
flames or?
cold flame. HHO, Brown's gas, I guess you could call that a cold flame, which is another astounding technology or,
Right.
phenomenon that,
Wave it on your hand, but it'll
yeah,
sublimate tungsten on
yeah,
contacts, so that, yeah, so I don't know if they're talking about fire or if they're talking about cold flames. Yeah, I asked this question to Eric too, but it is a little bit kind of general, so
yeah.
I don't know what they're talking about. Um, let's see. Does anyone have a recent story of suppression for making a device or giving information, real suppression from an organized group, not just naysayers?
Uh, Suppression works in many forms.
Yeah.
Cold shoulders from,
Yeah.
you go out to find investors, money.
Yeah.
You go to, if you get up, the deal is, as I learned from watching so many other people, don't get up on the soapbox and claim you saved the world. Just get out there and do it with your family, your friends,
Mm-hmm.
It's like some of the mistakes we made early on was our investors, they had to get, quote, sprinkles of holy water from the priesthood. If some PhD didn't give us the blessing, they weren't going to invest. So,
Right.
we went down to these big universities and,
Mm-hmm.
very kindly got tossed right out the door because they could not explain what we were doing. And rather than learning,
Mm-hmm.
it was, that's where we learned when it comes to like universities and people in institutions, it's the rice bowl first,
Mm-hmm.
thou shalt not mess with my paycheck,
Mm-hmm.
politics and reputation second, and science runs a distant third.
Mm-hmm.
So they get paid to be the all-knowing, almighty, and gods of physics or whatever. So when
Right.
you're some barnyard experimenter comes along, even though you got every bit the brain power, every bit the knowledge, every bit the ability to research, look, analyze, you're not a member of the priesthood, so they throw you out. So don't worry about those guys. Just go do it.
Right.
Don't worry about getting their blessings or getting up on the soapbox or running up to the big companies. And you just, it starts at the ground first,
Right.
and then if you, let the world bring the people to you need,
Mm-hmm.
you find somebody that sees what you're doing and sees the need. Maybe they got a few bucks, maybe they want to take it somewhere,
Mm-hmm.
and you just, just keep at it,
Right.
and that's why it's so becoming more and more publicly prevalent,
Mm-hmm.
Tell with the experts, they screwed the world up.
Right.
These common folks are going to fix it.
Right.
So that's why I keep saying go to the garage,
Mm-hmm.
look at Henry Ford, the Wright brothers, even Bill Gates. They all started in the little frickin' garage. Everybody telling her, when Bill Gates dropped out of Harvard, his parents thought he was nuts, right? He couldn't stand the academics.
Right.
But he had a great idea and he knew it. He knew what the future needed. It
Right.
was the same with everything else in the free energy world, Let's just do it. We got so much to work with, like, it's one I can't wait to get back to it. That's one of my things with Flyback was to get out there, create some great technology for the plant that was kind of interim, so then I didn't ever have to go find funding again.
Right.
I never had to go beg for, never had to go find an investor,
Mm-hmm.
never had to go find research dollars,
Mm-hmm.
and, to where I don't have to worry about a paycheck, feeding your face and keeping your bills paid and your kids fed while you're out there experimenting, you eating up all your time doing what you think's right for the world,
Right.
So that's, it's just, you gotta, if you use your smarts and think it through, you can, it's like, and people really, it's amazing. I can call it the power of the $5 bill. If you got one good inventor out there who's really got something going, and just to make the world a better place without expecting a whole bunch of returns, what's $5 a week? If you got 100 people dropping $5 a week to support a guy's work,
Mm-hmm.
That's $500 a week. That's like $25,000, $50,000 a year.
Mm-hmm.
From $5 a week. So
Right.
you give up a milkshake, a McDonald's burger.
Mm-hmm.
What's $5 a week?
Right.
From 100 people to support one good inventor.
Right.
And guaranteed that guy's going to, if he makes something go and makes something good, he's not going to forget you.
And this concept of the crowdfunding, like
That's a great
Kickstarter
one.
campaigns, Indiegogo, where anybody can start a campaign, raise funds publicly from whoever wants to donate to the cause.
Exactly.
And I mean, that's been gaining so much momentum over the last couple of years.
It's
and,
exactly what I'm talking about.
so-
You know, you take guys like Jim Murray, man, what a brilliant guy, you know. You know, I guarantee you give him $500 a week, and it's all gonna, you know, he's gonna make, you know, he'll put it to good use, you know.
Right.
And there's so many guys out there like that. If they just had a little bit of funding, you know.
Sure.
I mean, and the public needs to, you know, separate the charlatans from, you know, because
Right.
there's always the guys out there trying to, you know, the operators.
Right.
But here's what I found out about it, you know, the operators always dress too good.
Yeah. Right.
Take the guys in the dirty T-shirts and scroungy beards and don't care about appearances or making, you know, and a lot of times they're not the best spoken people, but they have brilliant minds and they got great ideas, you know.
Right.
So it's learning to sort the wheat from the chaff
Yeah.
and support those guys
Right.
that are doing something that really, you know,
Right.
that have great
Right.
ideas.
Well, yeah, I mean, the reason that we have the speakers that we had at our conference is because they're all builders and have been for years. You
Yeah.
know, and I've personally seen things, you know, with my own eyes. You know,
There you go.
John's been doing it for years. You have the shop with stuff you're doing out there, and you know, the lab, and you know, Jim Murray's been building for years. You know,
Yeah, there you
prototype
go.
upon prototype upon prototype.
Exactly.
You know, so it's not just desk jockey stuff with
Yeah, there you go.
people just talking about the ideas. So that's you know, that's what our goal is to have presenters, you know, like yourself, who making things.
Yeah, there you go.
You know, it's
It's like Lead Scallion's
It's
little,
tangible.
you know, magnetic motion holder. That's one of the simplest things out there to build.
right.
He published that in like the 40s sometime
Yeah.
when he wrote that book. And it works every freaking time, and you can't
Right.
take one physicist that
Right.
thinks he knows magnetics and have him explain that thing.
Right.
And when you take just common folks and they play with that thing for 5 minutes, they're never the same,
Right.
you know.
Yeah, it makes them think. I mean, you brought the model to the conference, and there's
Yeah.
a lot of people playing with it, and you know, and you know, perpetual motion holder
Yeah.
has been online for years. There's videos, there's stuff
Oh, yeah,
like
yeah.
that. But when people because I saw a lot of people, you know, around that little model,
that's what
playing
it was
with
for, play,
disconnecting
man.
it, you know, put it back on, touch the battery, let go, and
Yeah, it was something I
it
could
was
bring
fun.
that didn't require 160 volts DC.
Right.
Because I was, damn, you know, liability issues, you
Right.
know. Didn't
Right.
want to shock anybody, but I think
Yeah.
I'm going to do some for the next conference and stuff is, you know, it's one thing about electricity, it will zap your ass. It will
Right.
kill you if you're not
Right.
careful with it. But
Right.
that was, you know, 27 volts worth of 9-volt batteries, so
Right.
no big deal there. And people could
Right.
play all day long and they didn't have to worry about them zapping themselves, you know.
Right.
But
Safe,
it definitely, you know, makes people think, you know, and I watch
Right.
some PhDs, professors, chemical engineers, you know,
Right.
what are you doing?
Right.
Well, break the circuit, pull it apart, and I'll put it up there. See, it doesn't hang anymore,
Right.
you know, and it definitely relates to, you know, I don't care what, you know, it's modern lines of force. The standard theory is electrostatic lines of force and magnetic lines of force consist of nothing. Wrong. You know, it's just like the shirt. You know, we have a shirt, but it's the threads that hold it together, right? And they're the threads that hold it together, and they actually are gyroscopic particles, just like Lead Scallion said, just like Newman said. They have gyroscopic properties. They interlace with each other, and they're perpetual. They go and go and go and go and go, right? And so that's a perfect thing. You know, you get a loop of gyroscopic magnetic particles running in that loop, and they just keep holding that up and defying gravity forever and you know. They are perpetual. And it's the driving force, and it's just a really great theory. And that's what I find is Tesla's right on the money, Lead Scallion and Newman are right on the money, and all the phenomenon relate to each other. And they're all right. Every one of them's right, you know, and it's just defining it and using it.
And the difference with Newman is he's using, you know, miles of small wire, where you went the opposite direction, going big wire.
Yeah, I was
Yeah.
trying to beat resistance,
Right, right.
you know.
So
And Newman's got, you know, and that machine up there is Newman inspired, right? The coupling in space, that was one of his concepts. And, you know, you know. So it was all, you know, when
Right.
it just that reading that 20 brilliant pages in his book, and he's done some brilliant work since. I mean, he's kind of an ornery guy,
Yeah.
you know. He's you know, gets on the soapbox a little bit, but he's just this brilliant guy, and his gyroscopic particle theory is hard to argue with, you know. And electrostatic lines of force and magnetic lines of force are they're the same thing. One transforms into the other. That's why I look at it like the Tao, right? You know, the religious symbol, the Tao, you know. That is a perfect representation of electromagnetism. One transforms into the other.
Right. Yin yang.
Yin yang, yeah, exactly. And so electrostatic lines of force are just rearranged magnetic, you know, gyroscopic particles, and one transforms the other, and it's just a switching of particles, right, in perspective and spin. And when you look at his model, it's freaking brilliant, and it really works,
Right.
you know. And you know, he has, you know, his theory is that it's 100% nuclear decay, right? You have 100%, you know, that you're actually decaying the molecules of the mass, your conductive mass, or you're decaying the mass. You're taking the magnetic particles spun out of that mass, you're using them, you're taking them out, because E is equals mc squared. It take you hundreds of years to notice any depletion of mass. You take Tesla, and you know, you're pulling it out of the ether and transferring it through.
Right.
Well, who's right? It doesn't really matter,
Right.
you know. But somebody's going to have to do some experiments to see if it actually does deplete mass. You know, if it doesn't
Right.
deplete mass, well, then Tesla's a little more to the right side. If it does, well, then Newman's got it. It is 100%
Right.
nuclear. But either theory, it works.
Right.
You know,
Yeah, I don't
so,
think we'll live long enough to.
yeah. Or really pull some power out of it.
Right. Let's see. Could you talk about 100% efficient transformers? Why we don't make them? And it says anymore, and what might we use them for if we did? Have you ever seen a 100% efficient transformer?
Well, not as long as there's resistance in the wire, but I've seen them like our inverter transformer, because of our process of using that magnetic energy to do work, rather than letting it, see, if Mother Nature set it up to where when you build up that magnetic field and it becomes oppositional, it transforms to heat, heats the core. So what we do is we turn that to work, right? We give it a load and we keep moving that energy out and recirculating it back. So our transformers go to about 99% efficient. Where normally they're only 90% efficient because we take all the core heat out of it.
Right.
The cores actually run colder than the windings. So it just becomes winding loss.
Right.
So, and we've had more than one physicist and electrical expert. Go ahead, put your hand on that transformer. It'll
Right.
burn me. No, it won't. Put my hand on top of it, it's
Right.
running full power, and they go, wow. And they touch it and they just can't believe, you know, and
Right.
they're looking around for, they think we're fooling them.
Right.
But because we're not letting that energy transform itself to, and that's our process,
Right.
our flyback patented process of taking that energy out, making it work.
Right.
So we get them darn close to 100%.
Right.
And if I had my super low resistance materials where I could get the winding losses out of them,
Right.
then really watch what we could do,
Right.
you know.
Right. Right.
But that's what we do, you know.
Right.
And just take that core loss out and make it do real work.
Is there some way, either from what we've heard this weekend or beyond, to take an electric car and make it capable of going indefinitely without another charge from standard sources? In any practical, easy way that you know of? I added that last.
Actually, yeah, it's going to take some research and some time to do it, but
But you see the possibility.
yeah. Well, it's like our motor up there.
Yeah.
We've proven it out. Once we did what we did, we killed, you know, well, I wouldn't say we killed it, but Maxwell's equations that say you can, you know, 749 watts is equal to 1 horsepower. Well, that's as if a lens is in play. So if I'm getting a horsepower for 100 watts, or 200 watts,
Right.
and I take a generator and tie to that thing, and I'm making, say, 720 watts, efficient generator, it means I got about 500 left over.
Making up way more than enough for the losses above just the
Yeah,
velocity.
so if I got a COP of 3, or whatever, well, and coefficient of power becomes meaningless unless you relate it to those laws, right? So that's just, but if I'm making horsepower for 100 watts, that means I got a motor to drive that car with a lot more horsepower for a lot less electricity. And then I can take a standard generator and actually create that, turn that horsepower back to electricity and have a net. And that's a direct conversion of magnetism to energy, motion and
doing
energy.
work.
Doing work.
Right.
So absolutely it's possible. So like this motor, every coil is 15 ohms. And we built it that way on purpose because our switching, we hadn't perfected our switching. That's why you see those neon lights on there to make our transition thing. But if you just, and so we were getting 3/4 of a horsepower for about the same efficiency as a standard induction motor. But if we just make the coils go from 15 to 7.5 ohms, that cuts the power consumption in half right there. Our energy capture gets up, and right there we break a COP of 1 right there just by taking those coils down. Because now we can get the same work for 80 volts rather than 160. So our 1,020 watts goes to 600 watts. Our head couplings in it is not nearly as efficient, so we could have made, if we fixed that, we could make 32 pounds of torque instead of 60 pounds of torque. If we increase the oscillator speed, we could get we can increase the RPM without costing us any more power.
Which that concept is already proven.
Yeah, exactly. So once you're there, then I got a generator, a standard Maxwellian-based, generator. Well, I figured out magically how to transform magnetism into energy by beating Lenz's law and all the other things we did. Well, now I can hook up that generator, loop out a couple hundred watts back, and I should have 500 watts left over to do whatever I want with. And that's a direct conversion of magnetism to energy, which, of course, when you say things like that, the physics community splatters off the ceiling.
Right.
Because they say magnetism is not energy, and it's just like blatantly a fact that it is an energy phenomenon. Getting it to perform continuous work, that's the trick, And I've seen, there's some YouTube stuff that's really funny, right? They got magnet accelerators, right, where you get a ball bearing and a magnet and a ball bearing, and you get them all lined up and you clip one, and and the last frickin' ball shoots out like it's a frickin' BB gun, right? But that's not energy.
Right.
And I go, no, that is energy. It's not continuous work, but it's an energy. You caused acceleration, and acceleration is an energy phenomenon. If magnet accelerates anything, then it imparted energy. So getting it to transform into continuous work, now that's the trick. And that's what that machine's about.
Right.
And that's why those neodymium magnets are so important. Because if we had to do that all with electromagnets, you'd be expending more. But because neodymium's so strong, we're able to create such high foot-pounds with it. So we're pushing on it with an electromagnetic field, but the neodymium's pushing back too, right? So it's contributing to the torque. So it's a transformation of magnetics into energy.
Right.
And we're reusing the electricity over and over again. We're not having to run voltage up because we've eliminated drag forces.
Right.
And we're able to clock speed up rather than, we're able to increase speed and horsepower without voltage input, and we proved it all. I mean, it proves the concept. So, when you translate the math into the next one, you go, wow, we make the coil resistance go down, we get the head coupling right, we get the drive frequencies up so we can get more speed out of it, and we're there,
Right. Which new energy technologies seem closest to being sold and accepted by the mainstream?
Sold and accepted by the mainstream?
Which new energy technologies seem closest to being sold and accepted by the mainstream? Any kind of exotic energy technology that seems it's actually getting out there in any serious way, or?
I have my suspicions, that the military loves it.
Yeah.
and they're not ever going to tell us what they're doing with it.
Yeah.
But to me, like electrogravitics is a proven concept and a matured technology.
Right.
They ain't going to lie to me and tell me different.
Right. Which they are using right now, and that's there's enough documentation out that they are doing that.
And that's all also, it's a, and that's a free energy technology right there. So I'd say the militaries around the world have embraced it and have been using it for at least 30 years and probably longer than that.
Right.
As far as the rest of us goes, status quo keepers in industry out there, and the banking cartels and everything, they've done all they can to beat it down and whip it out. But that's what we're here for, right?
Right.
So Brown's gas has made a little bit of headway, but as far as industries out there, they're all status quo. I just don't, Of course, I got surprised a little bit by our visitor from Sweden, who's embracing some of this stuff, and so there are some companies out there that have embraced it and proven it in their own labs, but they're being very, very careful about how they go about coming out into the world.
Right.
So I know there's a lot of work going on out there, but if it's a Fortune 500 company,
Right.
I mean, you got Canadian tar sand oil, fracking in the Dakotas, and the big energy interests are up to their old games,
Right.
But that's the question is, the military loves it.
What technologies and inventors in new energy are most exciting to you right now?
Oh God, I'm excited about the old ones. Like Jim Murray's great. There's there's so many guys out there. The same old, Bearden's still doing some great stuff. Newman's doing some great stuff. All the guys that have been out there have just been at it to where they're really got their concepts refined, and
Right.
So just the SG school, just that SG schoolgirl motor, to me,
Right.
for people out there to really want to,
Right.
to build something and make it go. That is just such a great concept because it's simple.
Right.
It works. It's simple. It's undeniable,
Right.
and that didn't exist 10 years ago.
Yeah.
And to me, that's one of the greatest.
Yeah.
It just works every damn time if you build it right.
Right. And it's still more and more is being learned about it, and
Oh, yeah,
John is always coming out with extra little things to help recharge the front battery, like he showed at the conference.
Yeah,
while it's
exactly.
running, and
Those battery
So it's,
curves he was showing, those real-time battery curves were hard to argue with. Both
Right.
batteries were going up, and he had load on it too.
right,
So it's
Right.
like, hey, that thing works,
right,
And I know there's some guys in Australia who've taken that concept, and they're about commercialized.
yeah,
But they're kind of like flyback, it's a tough row to hoe because you're out there.
right,
The system's designed to keep funding out of your hand. Can't, it's if you're out there trying to raise the funding, the system is designed to rob you blind, rob inventors blind, shelve the technology, or one of my uncles, he invented about half the farm machinery used in America, and he was working with a company called Hydroslip. Well, he signed a contract with them. They funded him. He got it all done. Time to go into production. They said, we're going to shelve it for a while. Little did he know, his lawyer missed a clause in his contract that said after 7 years they owned it all, and he wasn't due any royalties after 7 years.
Right.
And this lawyer didn't catch it, and it was in the contract he signed, and
Then
they
started
just
making it.
they just shut it down and waited him out 7 years, and the second the 7 years was up, they showed up, grabbed all their stuff out of his garage, and started manufacturing, and all to beat him out of a 3% royalty, and they did it and got away with it. So,
Right.
that's why, it's going to take some people to go out and butt heads with the industry like we do,
Yeah.
where we're creating stuff that's useful and fits into the fits into the alternative energy markets as an interim step. and then, you know, and keep pushing it. But it also takes the cottage industry guys too,
Right.
right? So and one's gonna feed the other, right?
Right. Well, that's all the questions from these. And today is July 15th?
Yep, the 15th. Yeah.
Today's Monday?
Monday the 15th,
Monday,
yeah.
okay. And so Paul's talk is scheduled for release actually 2 days from now, day after tomorrow, on Wednesday the 17th. It'll probably be early afternoon, and it will be at the exact same website, magneticenergysecrets.com. And if you go to magneticenergysecrets.com right now, all you're going to see is just last year's talk. But on Wednesday, this year's talk will be on there too, so you can either get the first one. On Wednesday, you'll have the choice to get the first one or the second, or get the combo pack of both talks at a discount. And so we'll be sending out notices as soon as that's available. And so is there any final message you have for anybody? Or
Peace, people. Keep at it, man. Experiment.
All
We're
right.
winning.
All right. Well, thanks for listening, and stay tuned for a couple more interviews coming up with the other speakers at the conference. Thank you very much. Inventor
Yeah,
should come
yeah,
up.
exactly. It always comes up, yeah. And
Right.
there's about 14 patents out there, but
Yeah.
spread around the world. But the three main big ones always pop up first. So
And are those patents mostly related to the high-speed switching circuit you developed and the motor? Or is there other-
architecture, it's electronic architecture was the first one. That's the first one we had to get done because everything's based in that.
Mhm.
And then we had what was our mini microgrid technology, some of our inverter technology that we took that switching and created, and our mini microgrid, and a bunch of our technology that we integrated. Very extensive patent, about 80 pages.
Mhm.
And then the real third one is the motor patent, which is where we take that same switching and use to create the externally coupled motor that we developed.
Mhm.
And so they're all out there if you sort through them.
Right.
You know, sometimes the patent office makes you pay for the drawings now, but they're there and all the claims and everything. So
Right.
it's time to let the world know about it now. So
Right.
it's not the patent world is a world unto itself, you know.
Right.
And
So with the motor, for example, like last year, you just kind of talked a little bit about it, but since the patent's been granted at
well, it hasn't been granted yet,
or-
but it has
okay.
been published. Yeah.
The application is published.
Yeah. Exactly.
Okay, and since that is publicly available and people can actually see
Mhm.
it,
Yeah.
at this year's conference, you actually explained a little bit about the operating mechanism behind it and why it's.
Yeah, there's bunches of different mechanisms. Well, we spent years in the lab, and we built that one, you know, in our home labs.
Mhm.
And we built that motor to express everything we had learned in one device.
Mhm.
And that motor has actually, now we finished it in 2000, early 2003, so it's been sitting there for 10 years. But
Right.
we thought we'd be able to go out in the world with that motor explaining everything, and it really just befuddled. It was just, you know, we really got beat with and pelted with rocks more than we got a warm reception over it because
Right.
it was so radically different. And,
Right.
you know, the claims that we were making about external coupling and,
Mhm.
you know, the whole the whole concept is that electricity can be used multiple times. You can make work with electricity, get that electricity back, and make work with it again and again and again.
Right.
So it was built to prove that concept.
With just a little bit of. Hi everybody, this is Aaron Murakami with the recent Bedini-Lindemann 2013 conference in Hayden, Idaho. And you might know me from Energetic Forum and Energy Science Forum. And myself and Peter Lindemann have been publishing some different books and video presentations through emediapress.com, and which is where the different presentations from the conference will be made available. So right now, this is July 15th, so we're about a week.
2 weeks.
Actually 2 weeks from the conference, which we had on June 28th, 29th, and 30th. If you do want to see a little bit more about what that conference was about, who the speakers were, what the schedule was, you can go to EnergyScienceForum.com, and at the top of that there's a banner for the conference you can click on, and that'll take you to all the speakers' bios and everything else. Sitting with me here is Mr. Paul Babcock. He is the founder of Flyback Energy, and if you know about our conference last year, which was about the same time of year up in Hayden, Idaho, Paul gave a talk called Magnetic Energy Secrets, where he went over some of the technologies he's been involved with, different experiments using plasma over an arc, using inductor, with an inductor, without, showing, for the same amount of input you're putting in, you're able to get more work done, burning down a copper rod.
Hotter arc,
Paul,
more energy.
And so, and this year you went over a little bit more about that. And one of the differences from last year is you alluded to a motor that you're working with, because your company has, when I first met you, it was several years back, and you were still in the process of filing for some patents on your switching circuits and that motor.
Yeah.
So you couldn't really talk a whole lot about it, or even mention very much last year.
Yeah, at least till the patents were published.
And so,
once they're published, then I have no problem talking about it.
Right.
Because it's public information after that. So.
Right. And so so if anybody goes to a patent database, and if they want to see some of the switching circuits and the motor that Paul is involved in, you could type your name, Paul Babcock, as the losses, so you just make up for the losses.
So we're making up for the losses.
Right.
And also about beating Lenz's law and taking out drag forces out of motors, right? So it was all about rearranging Maxwell's equations,
right,
and Faraday's and Lenz's equations, and saying, hey, if we can externally couple, figure out how to get the same foot-pounds or equal to force out of a motor, by driving externally coupled fields, if we can get enough foot-pounds, that we can actually build different motors with different curves, right?
Right.
To where if we don't have drag forces, we can actually increase the speed of the armature because it's clock driven, it's not voltage driven like a standard motor is. You turn the voltage up, it goes faster. But of course, so does your watts. So we fire the coils of a high frequency pulse, which gives us, and it's pulse width modulated, so it gives us a very precise torque control.
Right.
But when it comes to making the armature go faster, we turn up the clock speed. We don't turn the voltage up, we turn up the clock speed.
So it's the same going in.
Yeah, so we maintain the same torque, but as the RPM goes up, the horsepower goes up. So, so we flattened out the curve. We actually do have a little bit, some drag force in there. We got about 80% of it gone, and if we had it perfected, it would probably be even much more efficient than that. But we showed how we can make things go faster and faster, increase horsepower.
Right.
With very little inputs, increases of input power, which of course that was a good beating from the academics over that one.
Right.
And then we recovered all the energy off the coils, or 50% of the energy we recovered off the coils. So we have videotapes. In fact, I was going to do them at the demo, but I couldn't find them. Of about how we actually have the motor set up to where we can actually feed the power recovery out of the coils out to resistors, and you can measure that power. And they get hot, plenty hot, and then how we just flip switches and we reroute that power back to the input to the system.
Right.
Now the power just drops down 50%, but the load maintains perfectly.
And so in simple terms, a lot of people who have followed the so-called free energy field and looking at these exotic energy technologies, it's pretty well known by this time by a lot of experimenters that you can charge a coil, get work, turn it off, that field collapses, and normally you'd get
an input source. So it radically jumps up efficiencies.
So you're like double, triple dipping into the same
exactly.
We're
making it work. We're making that field work even after we've disconnected from the source.
Right. And so taking that capacitor and being able to put it onto the coil fast enough is where your patented special switching circuit comes in.
Exactly.
So,
and we also had to make it tough enough, because we run big inductors. That's why high frequency switching came along, is because if you take your average transistor and you hook it up to a big inductor, that magnetic field just turns around and eats your semiconductors.
Yeah.
It was why high frequency switching came along, because nobody could figure out how to run big inductors reliably with transistors. So that's why we created our switching architecture to where it actually duplicates mechanical switching. So when it's off, and it's high impedance. So when that field collapses,
Right.
it's tough. It can live through those big inductors because
Right.
I mean we run big inductors. You know,
Right.
we don't mess around. You know, we got big transformers and
Right.
big coils
Right.
and while we were developing this, a lot of different stuff came out about it, magnetics that's just not taught in the books, like it's what we call reduced impedance effect and other things. So reduced impedance effect is there's two ways you can make magnetic fields. You can run lots of current through wire. You know, you can run, you know, the more wire you have spun on there, the stronger your field, or the more current. You know, the problem is with more wire is you get inductance, and then when you try to put high frequency pulses through it, it rejects. So you can't build up the high, you can't, you know, the old way was you couldn't build up a high, strong magnetic field from lots of wire because you have the impedance, you know, good old Henry's opposing your input source, so you couldn't get any current through it.
Right.
But with this high-speed switching system, we call it zero stating the inductor, where when we de-energize that puppy, Mother Nature gives you a freebie. The very first pulse, it'll let you run current through it until you get a magnetic field built up that turns oppositional to you. Just good old Lenz's law, it's just bucking against you. It's Henry's. And so that first one's free.
Right.
But after that, it takes voltage to drive current, and then you...
Spike out of it.
Mm-hmm.
So instead of that, you're able to do something special with that spike and
Right,
control it
it's-
to do more mechanical work.
Exactly, and
Yeah.
recover energy at the same time. So
Right.
if you let that spike go, you know, if you just turn the circuit off, what you get is that high spike of energy,
Right.
A high voltage, low current, high voltage spike, because it's
Right.
all about the velocity of the field collapse. It's dV over dt, you know. Faster collapse, the higher the spike.
Right.
So we created this high-speed switching system. The magnetism is fast, right? I mean, you got to be fast to get a switch connected to that.
Right.
So otherwise, that energy's transformed itself to high voltage instantly, right? I mean, it's, you know, so if you're not faster than 50, 100 nanoseconds to get a full, what we call our capture circuit, we call it fire and capture. Fire is energize it, and capture is to grab that energy that's built up in the coil. So we figured out how to make that switching transition from fire to capture in a matter of nanoseconds. So what it is, the voltage never gets to shoot up to that high voltage. So we actually dump it onto a capacitor and give it a low impedance load. It's always the same joules, whether it's a high voltage low current or a low voltage high current, but we give it just the right load to where we control that collapse and control that voltage level.
So it collapses slow, but the current is still there.
It's still, that magnetic
So
field's
the
still
magnetic field is there to push
Right.
or pull the magnet,
exactly.
whichever way it's
So we're
wired.
getting work out of it, right?
Right.
And then while we're doing that, we're
Which means
charging.
it's disconnected from the input.
Yep, we're getting work while
So-
we're disconnected from the input, right?
Right.
We're making that field still perform work while it's collapsing,
Right.
but we're also charging up that capacitor. And so the
Right.
trick is to charge that capacitor up to the right level to where we're 20 to no more than 30% over the input voltage. And then right in the beginning of the next cycle, that capacitor discharges first before we draw from the input power. So all that magnetic field is constantly circulating back in. It's performing mechanical work, and then
Right.
it puts, and so while it's doing that, while you're disconnected from the source, then on the beginning of the next half cycle, it dumps that cap and performs mechanical work again before we
Right.
dump on the source. So both ends of the waveform
Right.
are work that's built into the coil
Right.
rather than just 100% from